Okay, so at the end of the last video, we introduced Frobenius' theorem, and we're going to establish an example, or we're going to work through an example that sort of uses this. I do want to mention one thing. I was kind of tripping over my words earlier when I talked about this interval. This capital R does not mean the same thing necessarily that it meant in the previous section. I misstated that. It's just some positive or some non-negative number. Establishing a radius of convergence for this thing. So just think of that as just some number that makes an interval out of this. It would actually have to be positive, not non-negative. But anyways, I digress. So here's the DE that we want to solve: 2xy double prime plus 5y prime plus xy equals 0. And as we can see, that the point x equals 0 is a singular point of this function. And we're told in the problem that it is a regular singular point. You can verify that yourself, given what we did in the previous example. But we're just going to let the fact that they tell us that be enough and move on to solving this. So what we're going to do is try to find a solution that takes this form. That's what Frobenius' theorem says that we can do. And in our case, the singular point is x equals 0, which means x naught equals 0. So this takes on an even simpler form. Y, we're going to assume, has this form to it. N equals 0 to infinity, Cn x to the n plus r. And remember, r is a constant that we're going to try and figure out through this process. And I lost my train of thought. That's all I think I wanted to say there. So now we're going to look at derivatives, and I want to pay close attention to something that happens when we take the derivatives of these guys here. So this is going to be n plus r times Cn x to the n plus r minus 1. Now back in the second section, 6.2, when we would take a derivative, our index would change from n equals 0 to n equals 1. And the reason for that is because when you differentiate this power series, the constant term, the term corresponding to n equals 0 is going to go away. That's what happens when you differentiate a constant. However, these things are not necessarily power series, and it's because that r is not necessarily an integer. In fact, even if it is an integer, but just anything other than 0, this thing won't even necessarily have a constant term. So differentiating it won't necessarily remove that first term, and we still start at n equals 0 now. Okay, so that's an important distinction to make. Y double prime, we differentiate again, still starts at n equals 0 to infinity, and we're going to have n plus r times n plus r minus 1, x to the n plus r minus 2. And so what I want to do is substitute this in to my DE, and kind of like we've done before, I want to try and combine everything into a single summation if I can. So our DE looks like this: 2xy double prime plus 5y prime plus xy. And now by this point we've done a lot, or at least a few examples of this process, even though it was without this r here. So I'm going to do some of the arithmetic ahead of time to save some time and space. So y double prime, here's my y double prime. Notice we're multiplying that by a 2x. Okay, so I'm going to go ahead and just do that right in the first step. What will that look like when I multiply it by 2x? Well, I'm going to get 2n plus r times n plus r minus 1. And then multiplying by the x will change this to x to the power of n plus r minus 1. Okay? Next up, I have plus 5y prime. Here's y prime. I'm just multiplying the 5 into that. So this becomes n equals 0 to infinity 5 n plus r. I forgot my Cn in there. Cn x to the n plus r minus 1. Okay, and then finally I have plus xy, so I need to multiply y here by an x. This becomes plus n equals 0 to infinity cn x to the n plus r plus 1, now that I've multiplied another x into that. Okay, so 3 series that we need to combine. The first 2 match up perfectly. Notice all of the indices start at n equals 0, and that always happens when we're doing these problems for the reasons I mentioned a little bit earlier. However, they don't all start at the same x term. Notice this guy, if I plug in n equals 0 right here, it's going to start at r minus 1. Same thing here. If I plug n equals 0 to get that first term right there, it's going to give me an r minus 1. So both of these series start at their x to the r minus 1th power term. Whereas this guy, if I substitute a 0 in for n here, starts at the x to the r plus 1th term. So that means each of these guys, each of these series, is going to start with the term x to the r minus 1, and then you plug a 1 in for n, and that's going to give you x to the r, and then it's not until you plug in a 2 for n that we get x to the r plus 1, which matches with the first term of this series. So what that means is that I need to pull the first 2 terms out of each of these series before I can combine those things in summation notation. So this is going to look like this. What do I get if I plug n equals 0 into this series right here? Well, I'm going to get 2r times r minus 1. X to the r minus 1. Okay, now if I'm going to go ahead and plug in the next term, because I know I'm going to have to plug in n equals 1 as well and pull that term out. If I do that, I'm going to get plus 2. This becomes r plus 1. This becomes 1 plus r minus 1, which is just r. And I keep forgetting to put my c's in there. There should be a c naught right there. This will be c1 x to the r. Okay. Now let's do the same thing with this next series. I want to plug in n equals 0 and n equals 1 and pull those first 2 terms out. So I'm going to get plus 5 r, when I plug a 0 in for n, c naught x to the r minus 1. And then when I plug a 1 in for n, I'm going to get plus 5, this time r plus 1, c1, x to the r. Okay? Having done that, both of these series here are going to now start at the x to the r plus 1th term after having pulled these terms out. So let's look at what those look like. I'm now at n equals 2 to infinity of this guy, to n plus r minus 1, cn x to the n plus r minus 1, plus n equals 2 to infinity, 5 n plus r c n x to the n plus r minus 1, plus this guy, n equals 0 to infinity, cn x to the n plus r plus 1. Okay, so it's a huge mess, I know, but what we're going to do is combine some like terms and stuff like that. So first of all, with these terms that we pulled out, I can collect the x to the r minus 1 terms first. So notice if I were to distribute this 2r in, I'm going to get 2r squared, and then 2r times negative 1 is negative 2r. But notice I'm going to end up combining this term to this term, because they both have a c naught x to the r minus 1 in them. So that minus 2r plus this 5r is going to give me plus 3r. And then I'm going to have c naught from both terms, x to the r minus 1. And then if I combine the x to the r terms, the c1 x to the r terms that I'm getting, I'd have to distribute the 2 in. So that's going to give me 2r. Bring that r in. That's actually going to be 2r squared. So plus 2r squared plus 2r right here. And then from this guy, I'm also going to have a plus 5r, so that's going to add up to plus 7r. And then I'm also going to have a plus 5 from this guy, so plus 5x to the r. Okay. Now the next thing I'm going to do is going to be to combine all of these series, and I'm going to attempt to do a lot in one step here. So if you're not happy about the fact that I'm doing this all in one step like this, there's some steps to fill in between here and here, but hopefully you can track with me. So again, to add these three series together, we've done the first thing that we're usually supposed to do. We've gotten them all to start at the same type of term, x to the r plus 1, as you can see by plugging a 2 in for each of the n's here and here. But now we need the indices to start at the same place, and so what we're going to do is try to replace both of these n equal actually, I'm sorry, we're going to replace this n equals 0 with an n equals 2. So let me change that. N equals 2 to infinity. That's where we want to start. So my first two terms aren't going to change, right? They're already starting where I want them to start. I notice they also have kind of like terms. They both have a cn in them. So what does that look like when I combine everything? Well, I'm going to do some combining, but also some factoring at the same time. Notice both of these have a factor of n plus r in them. I'm going to take that n plus r, and I'm also going to take the cn and just bring that out. So I have cn n plus r. What does that leave, though? Well, in this guy, if I remove that n plus r, and if I distribute that 2 into this, I'm going to get 2n plus 2r minus 2 out of that. Notice also I have this 5, which is all that's left after I remove the n plus r and the cn. I'm also going to remove the x to the n plus r minus 1s as well. So basically what that leaves me with is this 2n plus 2r minus 2 plus 5, so that's plus 3. And then the x to the n plus r minus 1 I'll bring out to that side. Okay, so this is what it looks like if I combine these two series and then factor things accordingly. This last series we would have to do a little work on because it's not starting at the right index. So if I bring n equals 0 up to n plus 2, by increasing this by 2, I want to subtract 2 from all of my n's here. So that we get the correct so that everything is equal to this series right here. Now I want to notice something if I do that. If I replace this n equals 0 by an n equals 2, and then if I subtract 2 from this n right here, this becomes n minus 2 plus r plus 1, which is the same thing as n plus r minus 1. It's going to match with this term. So let me actually remove this guy and then factor it out at the very, very end. If I also subtract 2 from that n right there, I'm going to get plus cn minus 2. And now all of that has an x to the n plus r minus 1 in it. All right. So far we've done a ton, and we're about halfway there, I would say. This is equal to 0 because that's what the original DE said. At this point, we know that this expression in here is where we're going to get a recurrence relation because all of the terms of this series are equal to 0 by that identity property. But we also have these two things to deal with. Now, I forgot my C1. I have the hardest time remembering to put those C's in there. So the next step that we're going to do is going to seem a little bizarre, I think, but C0 and C1, remember, we can kind of think of those as parameters. And I'm going to intentionally plug a 0 in for C1 so that this whole thing goes away. I actually only want to deal with the C0 here. And there's a reason for that. Remember, the goal here is to find two linearly independent solutions. And there's multiple different ways of doing that from this stage, but what I could do is if I plug a 0 in for C1, which is allowed to be any value I want to plug in, it's just a parameter, and then I deal with this guy, the next step of our process is going to involve solving for r. And you're going to see that we get two solutions for r, which we can then plug in to y up here, and that gives us our two linearly independent solutions. Basically what that means is that this term is unnecessary to find those linearly independent solutions. It's enough to just deal with this. So I'm going to take this guy, set its coefficient equal to 0, 2r squared plus 3r times c naught equals 0. Now again, the goal here is to solve for r, right? And remember, c naught is kind of like a parameter. It can equal anything. So it's not helpful if c naught is equal to 0, because that reveals nothing about r. So let's assume that c naught is not equal to 0. So if c naught is not equal to 0, then we have this factor equals 0. And let me factor that r out. R times 2r plus 3 equals 0. So we get two solutions, and I'm going to be calling one of them r1. r1 is equal to 0, or r2, which would equal negative 3 halves. That r1 and that r2 correspond to the two values of r that I can use in my solution up here. Okay? But notice, if I just plug in r1 and r2 in for that r right there, there's still the issue of finding the cn's, finding those coefficients. And so we still need to go through the same process we did back in 6.2. What I'm going to do, though, is handle this in two separate cases, starting with r1 equals 0. If r1 equals 0, then I can plug that 0 in for the r's that are appearing here and use that to find my recurrence relation. So if I plug in 0 for r, this becomes Cn times n times this is going to be 2n plus 0 plus 3, so that's 2n plus 3. And then this becomes plus Cn minus 2 equals 0. Or solving for Cn, I get Cn equals negative Cn minus 2 over n times 2n plus 3. That's the recurrence relation that I want to use. And notice, because this series starts at n equals 2, I need to make sure that we include that condition. We're starting where n is equal to 2 and working our way up from there. Okay, so let's remind ourselves of the assumptions that we didn't make. C naught is a parameter. All we've done is assume that it's not equal to 0. But now that we've done that, we can just call it C naught. So C naught is equal to C naught. C1, we've made the assumption that C1 is equal to 0, because that eliminates this term, and we're going to see that we still get two linearly independent solutions regardless of that assumption. Now I can start using my recurrence relation to find C2. So for example, C2 is equal to negative C naught over 2 times 2 plus 3, which is equal to 7. Okay. Now in the past, I've left this as a product because we're trying to establish some kind of a pattern. There's not an easily recognizable pattern that's going to occur here, and we're not going to try to put this thing in summation notation anyways. So this is one example where I will do that product. This is equal to negative C naught over 14. And how about C3? Well, that would equal negative C1 over 3 times 2 times 3 plus 3, which would be 9. But C1 is equal to 0. So that whole thing is going to go to 0. And you can start to see, just like we did in the previous section, we're going to get this alternating pattern between C naught terms and 0. C naught term and 0. So C4 is going to be one of those C naught terms. It starts out looking like this. Negative C2 over 4 times 2 times 4 is 8, plus 3 is 11. But this is the same thing as negative, or actually positive now, because it's a negative C naught over 14 times 4 times 11, which is equal to C naught over 616 when you do the multiplication. And then the C5 term is going to be a 0, and so on and so forth. So we already know what's going to happen the rest of the way there. Okay, so let's now look at R2, which was equal to negative 3/2. Okay, in that case, if I plug negative 3/2 in for my n's here, I'm going to get Cn times r minus 3/2 times, now this is going to be 2 times negative 3/2, which is negative 3, which will cancel with that positive 3. Oh, and I'm sorry, I'm looking at the wrong one. 2n is just 2n, but if I plug negative 2/3 in for r, it's off screen. Negative 2/3 in for the r right here. This will become negative 3, which cancels with that positive 3, and this becomes 2r. I can distribute the 2 in, and I'll leave the r out just so it stays factored. That's equal, I'm sorry, plus Cn minus 2 equals 0. I'm going to bring that 2 in and leave the r out. So this is the same thing as Cn times 2 times r times 2r minus 3 plus Cn minus 2 equals 0. Or solving for Cn is equal to negative Cn minus 2 over, these are n's, not r's. I keep getting myself all mixed up here. There we go. Yeah, sorry, those are all n's. N times 2n minus 3. So there's our recurrence relation. And we have some of the same solutions, or same assumptions that we're starting with. C0 is just C0, it's a parameter. C1 is equal to 0 by assumption. And then we can start finding these other values. So C2 is equal to negative C0 over 2 times 2 times 2 minus 3 would equal 1 in this case. So that's equal to negative C0 over 2. C3, as before, you're going to see this alternating pattern of zeros and C0 terms. So that's going to be a 0 as well. C4 is equal to negative C2 over 4 times, 2 times 4 is 8, minus 3 would be 5. Or this is the same thing as positive C0 over 2 times 4 times 5, which equals C0 over 40. And that's going to keep going. Okay, so now we actually have our two solutions, and they come from this guy. So what I'm going to do for my first one, we're plugging a 0 in for the r here. Notice that reduces this down to just a normal power series. Y is equal to C0, or C0, plus C1x, but C1 is equal to 0, so we lose that term, plus C2x squared, which will look like this, minus C2 over 14x squared. Let's call that Y1 actually. My next term is also going to be a 0, and then I'm going to have plus C0 over 616 minus ... It's this alternating plus minus pattern. So that's one of my solutions. Now Y2, I'm plugging a negative 3/2 in for r over here. And notice what that does. I can actually pull an x to the negative 3/2 power out completely from that series. So let's do that. I'm going to have x to the negative 3/2 times, using the coefficients that we found here, I'm going to have C0 minus C0 2 over x squared. Notice the x term is going to be a 0. Plus C0 over 40 over x to the 4th. I forgot to put my x to the 4th up here also. So again, we're only getting these even powered terms because of these alternating zeros here, minus ... Okay. I could also factor the, that should be C0. I can also factor the C0 out completely, or since I'm only really looking for two linearly independent solutions and not necessarily trying to put this in the form of a general solution, even though I could, we can just leave the C0s off, set them all equal to 1 or something, and call those my two solutions. But this also works. I can write it like that if I want. Okay. Obviously, this is a very lengthy process. It was already a lengthy process back in section 6.2. but the process is even a little bit longer now because we're dealing with different possible values for this number r that we've included in our solution. Of particular importance, though, is this guy right here. So remember, this came from the coefficient of my lowest degree term after combining all of the series together. Notice all the terms in this series are going to be of higher degree than x to the r minus 1 and x to the r. So the lowest degree term will have this coefficient. It'll involve a c naught, but if we ignore the c naught because we're setting it equal to something that's not 0, and then set the rest of that stuff equal to 0, it produces this equation that gives us these two values of r1 and r2. That's called an indicial equation. I'm going to define that right here. So here it is again. The equation that we found, r times 2r plus 3 equals 0. In that previous example, we call that the indicial equation of that problem. And the solutions of that equation are the indicial roots, or sometimes we just call them exponents, of the singular point in that dE, x equals 0. Those indicial roots are needed to solve the problem. Now, it took a lot of work to get to the point where we found that guy, but we can actually find the indicial equation and then the indicial roots for a problem like that faster than than when we were able to do it before. Now that we know that we're looking for that specific equation, there's a way to come up with it more quickly. So I do a little description right here where I talk about the stuff I just talked about. But remember, if we're talking about a regular singular point, which is the kind of singular points that we're doing these problems with, and this is the dE that we're solving, that general dE. In the definition of a singular regular point, p of x, we define a function lowercase p of x equal to x times p of x. And we said that if x is a regular singular point, then this function has to be analytic. Same thing with x squared capital Q of x. That has to be analytic at 0 also. So we would define lowercase q of x to be equal to x squared times big Q of x, and that's analytic. Analytic meaning that both of these functions should have power series that they are equal to. So if that's the case, both of these functions are analytic, and so they're equal to these power series. What happens if we make some substitutions in our original dE? Well, if we take the original dE, remember this guy, if I multiply everything by x squared, I would get this, x squared times y double prime, x squared capital P of x y prime, which I could write as x times x, and then x squared capital Q of x y equals 0. And my reasoning for doing that is because I've made this x P of x term show up and this x squared Q of x term show up, both of which I've said something about up here. So this x P of x in square brackets I could rewrite as little p of x, and this x squared Q of x, capital Q of x, I could write as little q of x, and then just rewrite this dE that way. Okay. However, both little p and little q, we have series that we've defined for those up here. We're using the assumption that they're analytic to do that. And if I were to expand little p of x and little q of x out into their series and then evaluate each one of these terms, and if I also make the assumption that y is equal to a power series of the form that we see in Frobenius's theorem, this thing, then I could put a series in for y, y prime, and y double prime and start multiplying things out. So for example, this first term right here, x squared times y double prime, would look like this. X squared times, this is what the series expansion for y double prime would look like. You can compare this to the summation notation that we found in the previous example for y double prime. Now I'm only showing the first term here, and then I say plus dot dot dot, and that's for a reason. So the very first term in that series would look like this. Multiply the x squared in here, and that's going to change that x to the r minus 2 into x to the r. And so the first term of this series would look like r times r minus 1 c naught x to the r. The x p of x y prime term, if I put the series for p of x in and I put the series for y of y prime in, we get something that looks like this. x, showing up here, times, remember p of x was equal to a naught plus a1x plus a2x squared. I'm only showing the first term, a naught. And then p of x, y prime, if you do the differentiation up here, would look like this. This is the first term, r c naught x to the r minus 1 power. Multiply that x in to this series, making that first term look like r c naught x to the power of r, and then multiply that also by this a naught here to get the first term of the product of these two series. And I would get this as my first term, plus a whole bunch of other terms that are going to result from multiplying these two series together. But again, we're only going to be interested in the first term here. Finally, q of x times y. Q of x was defined to be a series up here, and so its first term is b naught. The first term of y is c naught x to the r, coming from this right here. And so multiplying these two series together, the first term is going to be b naught times c naught x to the r, plus a bunch of other terms that we're not going to end up caring about. Now, why did we do this? Well, as we saw in that previous equation that I mentioned before, that indicial equation is exactly what we get from the coefficient on that lowest degree term, the term that has the c naught in it, after plugging everything into our dE. Well, these three terms show up as the lowest degree term in each of these guys. They're all common, so I can add them together, giving me this times b naught x to the r, right? But the indicial equation just gets rid of the c naught and the x to the r and leaves me with this guy. So again, these three terms, when added together, and we discard the c naught and the x to the r, gives us this as our indicial equation. R times r minus 1 plus a naught r plus b naught equals 0. So if we're able to determine this, then we can solve for r earlier in the problem than when we did in the previous example. I'll talk about this in the next video. I've gone kind of over my time here.